Hello and welcome to part 2 of our atmosphere topic, where we're going to have a look at the variations in solar insolation. In part 1 we looked at the global heat budget, where we had 100% of our energy come from the sun, but only 51% of it actually reached the surface of the earth. Now that isn't true across all the areas, and actually there is variations in our planet. So if we look at this first diagram, you will see that between the equator and 35 degrees north and south, there is actually a surplus of energy, and beyond that side, the 35 degrees, there's actually a deficit of energy. So we're actually, for this section, we're looking at why there is this surplus in around the equator and why there's this deficit above 35 degrees north and south. So let's get going. Okay, so we have the sun here and we have our planet. The sun is not that small, it is just very far away. So, roughly, our equator is the closest point to the sun. That is really what's defined by it. As we go through this topic, we'll find something called thermal equator, which moves up and down, but that is relative to the fact that the Earth actually tilts back and forwards, depending on the time of year. So thermal equator, the equator is the part we consider closest to the sun. So because the equator is the closest to the sun, it gets the most, the sunlight goes in a straight line to it. Whereas at the poles, there is a lot less focus. So the area across that this light here is hitting and the light that here is hitting is a lot more focused at the equator. And we'll do what we did before and we'll label these up and we'll come back to them at the end. So that'll be 1 and that'll be 2. So that's our first variation, that the equator is getting a lot more focused light than the poles are getting, because there's a bigger area it's got to travel. Even this line itself is longer, so a small number of seconds that light has to travel is going to lose slightly more heat and lose more energy. So there's less energy making it to the poles. So that's numbers 1 and 2, that the surface area that the energy is hitting is either focused or a lot more spread out, so it gives that surplus or deficit of energy compared to each other. Number 2, we actually have to add in our atmosphere for this. So I'm adding in our layer of our troposphere as a purple dotted line. So what we've got for this one is that we can see that at the equator, the distance that the energy has to travel through is a lot less for the equator. So you have, if you remember back to part 1, we were talking about the atmosphere absorbs, it deflects, there's more clouds that absorb and deflect sunlight. So if you've got less distance to travel through, then you can have less of that heat as well. So at the poles, where you have a bigger atmosphere, you're going to deflect more, you're going to absorb more, you're going to have more clouds that reflect as well. So you're going to have less heat at the poles because of this, and because the equators get really short, tiny atmosphere. It doesn't really, it's still huge, but like, you know, comparatively to that, the poles, it's going to be a lot warmer because it's less heat getting deflected, less light's getting absorbed, or energy's getting absorbed away. So that's number 3 and 4. The amount of atmosphere that the light actually has to travel through is significantly different. So this is number 4, and number 4 is something to do we've had talked vaguely about before, and that's something called albedo. Now albedo is taken from like the word albino, and to do with white, and to do with the colour of an object. Now things that are white reflect more, and things that are dark absorb more. So if you have areas of a really dark, like forest, a dark ocean, it's going to absorb a lot more heat. And if you've got areas that are really white or really light, somewhere like snow, then you're going to have a lot more reflection. So let's have a think about where we might find that on our planet. Up at the poles in the north, we are going to have a lot more white because our poles are naturally colder anyway because of the reasons we've already looked at in terms of like the lack of surface area and because of the... Oh wait, I've lost the planet. So up at our poles we have a naturally whiter planet. That is our Arctic and Antarctic. Because remember, all of these things are happening at the North and South Pole at the same time. So we have these poles which are normally we'd expect covered in ice and snow, which are really white. So they occur at the North and South Poles. Naturally, they would happen because we've got this imbalance anyway, that we've got less heat and light getting to the north because of the length of time it's got to travel, the focus and shape of the Earth that is less focused in that point, and because of the depth of the atmosphere, it's making it colder. So then makes it really white. However, because it is in white, it's actually going to reflect more back out into space. So it actually makes it even colder. Whereas at the equator, we have really dark oceans. The majority of the equator is ocean, so like the Pacific, like the Atlantic, and even bits that aren't are like, then you could have stuff like the Amazon rainforest, which is like here and is really dark. So all of these things work together to absorb more heat. So that's going to be our numbers 5 and 6. Between the variations between the equator and the poles, or those that above 35 degrees north and south. So we've got one more reason as to why there is a variation in our insolation from the sun. It's not as extreme as this, however, that if we rotated our planet, if we had slight variations in terms of where our planet was sitting or where it was facing, then we might have a variation in that heat. So if I shunted the planet up slightly, then where that surplus hits is going to go further south. If I moved our planet further south, then that surplus is going to happen a little bit higher. Those variations are also felt in the deficit areas, that they might increase or decrease depending how far away from the sun they are. And this is actually what happens as our planet rotates back and forward and round about, that actually we have these variations as they go up and down and back and forwards. But normally, for instance, now we're looking at standard, and we have these 4 things that actually affect our planet. So what we can add in is we can put another dotted line through for our Earth's axis and label that up as number 7, so that we have all of our 7 features there. So that is the variations in our Earth's energy surplus or deficit. To get all that in, let's zoom out. So there we have it. There is our variations in insolation. So remember, if you want to match them up, our surface area is 1 and 2, our depth of atmosphere is 3 and 4, our albedo is 5 and 6, and then our Earth's tilt is number 7. So just explaining each of those in detail would get you sufficient marks. Hopefully that's explained it really well. Join us for part 3, where we see how these balance out, because if this was the only case, then those above 35 degrees north would always constantly freeze, and those at the equator would be constantly boiling. Whereas that's not the case. We do have some strategies in our planet that balance out. We'll look at these in parts 3 and 4 about how energy is redistributed around our planet. But until then,